In this lecture, we are going to be focusing on the concept of memory. This is the first lecture in a series of lectures. We have just recently concluded a set of lectures on pipelining, and then we are going to move on to memory, which is a very important aspect to computer architecture as well as for operating systems. In this particular part of memory 1, we are going to be focusing on memory hierarchy and the principle of locality. Now, what is the first thing that comes to mind when we talk about memory? Well, everybody wants infinite amounts, unlimited amounts of cheap and fast memory. The two most important aspects would probably be the fact that it should be unlimited and the fact that it should be fast. That's probably the top two. Now, I hope you can see that these are contradicting objectives, because the larger the memory, the longer it is going to take to search anything in that memory. So it will be a slow memory in that case. So these objectives are going to contradict each other. So what we can do is create a hierarchy of memories so that we can give the illusion of an unlimited memory, which is very, very fast. So in order to achieve this hierarchy, we are going to be talking about static RAM, dynamic RAM, a solid state drive, and a hard disk drive. You can probably add two more things to this list. One being a register, which probably goes at the top of this list, and another one which goes at the bottom, which is, say, a server. So what is a register? Well, it's a placeholder for multiple bits, right? So that is going to be the smallest amount of memory one can achieve. Then moving up, we have the static RAM, which is essentially based off of 6 to 8 transistors. And we have seen in Coco how we designed this. So that's going to be 6 to 8 transistors. So there are more number of transistors in a given area in the case of static RAM. But it is fast. So we commonly know this as our cache memory. Next, we have dynamic RAM, or we commonly know this as our main memory. And dynamic RAM essentially will have, in its design, will have one capacitor which will hold the value of the bit, and we might need to refresh the contents of that capacitor by having a refresh cycle, which is typically around 64 milliseconds. So that's going to be slower than static RAM because it needs a refresh cycle. And it also has a transistor which allows you to access that capacitor. This does not need a refresh. And then if you go down this list, we have a bigger capacity memory in solid state drive, which has no moving parts. You can also view this as a flash memory. Flash memory is based off of the electronically erasable and programmable ROMs. And then next on the list is your magnetic disk, which is your local hard drive. And then one might have a server that they can access on a network to store even large amounts of data. So that would be a series of variety of memory technologies that you can use in order to give the illusion that you can achieve unlimited amounts of fast memory. Now, if I just connect those two objectives to my technologies, I'm able to achieve unlimited amounts because of the presence of the largest memory in my list, which is going to be probably a server or in most cases a hard disk. But in the case of fast memory, I'm able to achieve the speed because of the limiting factor is going to be the speed of the cache or the register. Most likely it's going to be the cache. Okay. Now, the famous analogy to this when you think about memory is how do you search for books, say on a particular topic? In this case, we are going to consider computer architecture, say in a library. So you say you have a campus of libraries, and in each library you have several shelves, and you're right now sitting on a desk um, with several books in front of you, trying to write something about computer architecture. So the first thing that we will probably do is once you find that particular library, you will go into that library and pull out a collection of computer architecture books. And then you will take those books to your desk. Sorry, you will go to the shelves, search for those books, and take those books to your desk. Now, suppose we have sat down and we have just noticed that we do not have a book that is specifically addressing the concept of pipelining. So we are missing this book. What do? You go back to the shelves and look for this book, and then you bring that book on your desk. And most likely, you are going to find that pipelining book close to the computer architecture books that you found on the shelves. So there is going to be some correlation in terms of space. Now, if you do this, there are going to be very good chances that many topics that you needed, you are going to find it right in front of you on your desk. Almost all of them. Most of the time, you are going to be just using the books on your desk. You will not. The idea is that you don't spend time going back and forth between the shelves and your desk. So you rarely go back to the shelves in that case. So that's going to save you a lot of time, leading to a fast memory. Now, this saves you time compared to having only one book there and constantly having to go back and forth between the shelves to return it and then take another one out. So in this particular example, our hierarchy is campus of libraries, down to one library, down to one shelf, down to the books on your desk. Right. So that's going to be a very helpful comparison to understand memory. And then, as we talk about several concepts in this particular lecture, we will try to connect them to this particular real world analogy. So let's take a look at how we obtain that illusion of having unlimited memory and fast memory. So on the top here, we have several aspects of memory. We have the speed, we have the processor, we have the size of the memory, we have the cost per bit for that memory, and then the current terminology in that particular level of hierarchy. I find a quick diagram of a pyramid very helpful in this conversation. So let me just draw a pyramid, and on the top I have the smallest memory, and then on the bottom, the lower level, I have the largest memory. So in terms of speed, we are going from the fastest speed to the slowest speed. Our processor is going to be first talking to the smallest memory, which might be the cache, which uses the SRAM technology. And if we don't find something in the cache, we might try to look at the dynamic RAM or the main memory, which is the technology is listed out over here. And then if we don't find it in the dynamic RAM for some reason, we might have to bring it from the hard disk drive, which is at the very bottom. And obviously, the smaller the memory, the faster it is going to take you to search for any word in that memory. And the larger the memory, the longer it's going to take you to search any kind of word in that memory. So the speed is because of the size of the memory. Size, the smallest goes right on the top, which is right there, the upper level, and then the largest memory is going to go way over here, which is in our case the hard disk drive. Next, we have the cost per bit. This is not the overall cost. That would depend on the specific computer, but this is just cost per bit. The highest price is going to be for the cache, because now we have 6 to 8 transistors in the same amount of silicon, so you are going to have the highest cost because of that. Now as you go down, that cost is going to be lower and lower per bit. The current technologies are SRAM, DRAM, and users might include a flash memory or a solid state drive over here with relatively less access times to increase the speed. We'll take a look at some examples, numerical examples that talk about all of these things. Next, we have a picture over here which shows the processor, the CPU, and then we have a register file and static RAM in a box, which we are going to call that as the fast memory block, which is going to be our smallest block, smallest memory. And then we have another block which shows our main memory, and there are other blocks which we are not showing in this particular diagram, which are hard disk and solid state drive and the servers. So if you just think about the main memory over here, it's going to be bigger compared to the fast memory, and it's going to be slower in comparison to the static RAM. Now, how are these three aspects of this particular diagram going to compare? Well, for capacity, the register is going to have the least capacity, and the dynamic RAM is going to have the most capacity. And that is primarily due to the cost. And in terms of speed, the latency or access time, the fastest is going to be the register, and the slowest is going to be the dynamic RAM. And that is essentially due to the size. The bigger the memory, the longer it takes to access any word in that memory. And the last one is bandwidth. Essentially, what is the bits per second between the processor and the cache, and what is the bits per second between the cache and the main memory. Well, the cache, thanks to Moore's law, can be implemented on chip, which means that the processor can quickly access the information on the cache, so the bits per second is going to be much higher than trying to get things from off the chip. So I can say this is essentially due to cost and the wire delays. Clearly, the wires on chip cost much less and are going to be very fast. So on a particular data access, if the data belongs to the fast memory, that is going to give us the lowest latency or the fastest speed, which is in this case going to be limited by the static RAM. Now, if the data is not present in the cache or the fast memory, is going to lead to longer wait times or slower speeds, and that limiting factor is going to be because of the latency due to the dynamic RAM. So how are we able to create that illusion? The illusion is created because we are going to exploit patterns in the memory access. The way computer programmers access the memory, there are definitely patterns in that. Now, in terms of our library example, clearly you accessed a very small portion of the library's collection. On a particular shelf, there was a section in which you had computer architecture books. So we are going to see how it works when we compare instructions and data. Well, instructions usually follow each other. So most of the time you are going to be executing instructions one after the other, unless you have a branch instruction. When you have loops, then you would need to fetch in the same instructions again and again. So repeated fetching of instructions. That's another pattern. Loop indexes, they are accessed repeatedly. And memory arrays will often be accessed serially. And there will be many other patterns in terms of memory access which we can exploit and incorporate that into our memory hierarchy. Now this is a very good example of a real memory reference pattern. On the x-axis we have time, and on the y-axis we have memory addresses, say 38 all the way down to 18, and each dot on this particular graph denotes an axis. Now I hope you can see that there is a very good correlation horizontally of memory accesses. As you can see, this particular memory address is accessed a lot, as well as this, and so on. So there is a very good horizontal correlation of accesses, which means time. So memory accesses at the same location are happening again and again. And also there is pretty good vertical correlation as well. So there's a block over here which accessed several times. There's a block over here that's accessed several times. So that means that there is also a vertical correlation, which leads to the fact that we are going to have spatial locality, meaning we are going to be accessing memory addresses that are closer to each other often. So because of this horizontal and vertical correlation of memory accesses, we are going to build the principle of locality based off of this. So let's take a look at the patterns in time and also in space. So the patterns in time, we are going to refer to that as temporal locality, and then for space we have spatial locality. If an item is referenced, so temporal locality is the correlation that's horizontal. If an item is referenced, it will tend to be referenced again very soon. So in terms of our library example, if you recently brought a book to your desk to look at it, you will probably need to look at it again very soon. The second locality is spatial locality, which has to do with the space or the correlation with respect to memory addresses. If an item is referenced, then nearby items will also tend to be referenced very soon. So during an execution of a program, instructions and data references tend to cluster, as we saw in the real diagram. Over a long period of time, the clusters may change, but over a short period of time, the CPU is primarily working on small chunks of code and data. Chunk 1, chunk 2, chunk 3, and so on. And in terms of our library example, the libraries put books on the same topic together on the same shelves to increase spatial locality. All right, now let's take a look at a few more things regarding the terminology for memory hierarchy. So in this particular diagram, we have a CPU and we have an upper level of the memory. So this should perhaps be cache, and we have a lower level of memory. So let's say this is your dynamic RAM or your main memory. And things could go to the processor or things could go from the processor to the memory. So this is going to be a general diagram. Now let's talk about the terminology over here with respect to a hit and a miss. So a hit is the data is in some block in the upper level. So if the CPU wants a particular block, and if it is able to find it in the cache or the upper level, then that is considered as a hit. The hit rate is the fraction of memory accesses, which includes reads and writes, in the upper level. So ideally, I hope you can see that you ideally want this hit rate to be really high, 90%, 95%, 98%, as high as possible, so that you mainly are interacting with the cache and rarely have to go to the main memory. So that's the hit rate. Hit time is the time that you are going to access the upper level. This includes the RAM access time and the time to determine whether it's a hit or a miss. Next, most of the time you might find the block in cache, but if you were interested in block Y, you do not see a block Y in the cache. So in that case, you will have to bring block Y from the dynamic RAM to cache and then get it into the CPU. So that's going to be considered as a miss. So a miss is when data retrieved from a block is in the lower level. Miss rate is going to be 1 minus the hit rate, and the miss penalty is going to be the time that you need to spend to replace a block in the upper level plus the time to deliver the block to the processor. So that includes both those times. Now let's see the memory hierarchy in action. At the top we have the processor or the CPU, then we have a 1 megabyte cache implemented using the SRAM technology, and then we have a 1 gigabyte main memory implemented using a dynamic RAM. So if our hit rate is 96%, that essentially means that the processor is able to find the block for 96% of the times inside the cache, and only for 4% of the time it needs to access the main memory, bring that block into the cache, and then can access that or can read that. But the first thing that is going to happen is the processor is going to try to see it in the cache. It's going to try to look at the local copy in the cache. 96% of the time it is going to find it here because we have a hit rate of 96%. 1 minus 0.96 is going to give us 4.04. So 4% of the time it's not going to find it in the cache. That's an average. And it's going to try to look in the main memory, and the data is going to be transferred as needed. So when we have a cache miss, we are going to look at it in the main memory. So if we had a cache miss, we are going to bring that block to the cache, and the processor can now get the word from the cache and then be able to read it. Now, it could also happen that we might miss it. We might get a miss even in the dynamic RAM. If that is the case, if we get a miss in main memory, we'll have to look it up on the disk or whatever is lower to the dynamic RAM. It could be solid state drive or it could be directly a hard drive. If the word is here, an entire block of memory containing the word is fetched from the main memory and put in the cache. So we don't get just one word, we are going to get the entire block. Let me highlight this blue. We are going to get the entire block, and we are going to replace the entire block in, say for example, over here. Now the important question is, why do we do this? We are doing this because we want to leverage spatial locality. Because if we are accessing this particular word, there are very good chances that we will also need that word or that word, something that's close by. So to leverage spatial locality, we are going to bring in the whole block. Now let's take a look at some hit rate and miss rate and how much time you are going to have to spend in accessing a word or a block. So let's see. If the CPU is looking for something in the cache, depending on what the hit rate is, for good amount of time it is going to be able to find it in the cache, and we'll have to include the cache access time as the total access time in that case. Or if we have a miss in the cache, we will have to look at the cache access time and add the time to fetch the block from the dynamic RAM to this. And two things might happen when you're looking at the dynamic RAM. You might get a hit in the dynamic RAM, which is the hit rate of the second level, or you might get a miss even in the dynamic RAM, so that you have to go to the hard disk. If you have a hit in the second level, which is dynamic RAM, then the total time will be the first level cache access time, and you'll have to add the time to fetch a block from the second level cache. If you have a miss in the dynamic RAM, then you will have three times now. One is the cache access time, time to fetch the block from the second level, plus time to fetch the block from the DRAM. And then it keeps going down because you have lower levels in this hierarchy. All of these times will become slightly more clear when we look at a numerical example. Now, a quick note over here. A memory read and a memory write are going to be very different. If you are reading, you have these two statements. You could hit or you could have a miss. When you're writing to memory, you could have a hit or a miss as well. So what does the read hit mean? Hit mean, if you're trying to read a particular word and you're able to find it in the cache, then you have to pay no penalty. That's a read hit. And if you miss it, that means that the word that you're looking for is not in the cache. In that case, you will have to stall the CPU. You'll have to fetch the block from the main memory to the cache and then give it to the CPU and then restart the instruction. That's a read hit and miss. Now, if you are, say, executing a store command, store instruction, you're writing to the memory, you could have a write hit or you could have a write miss. Write hit essentially means that whatever you're trying to store in the memory, that particular data is currently available in the cache. So in that case, you just update the main memory. If the data that you're trying to store to memory is not present in the cache, that is considered to be a miss. In that particular case, you would read the entire block from the memory into the cache and then write that word into that particular block in cache as well as memory. So the same copy is present in both cache and memory to ensure consistency. We'll take a look at both a write hit and a write miss later on in this particular lecture. And let's take a look at some numbers here. We are going to be focusing on the impact of computing system performance. Now here is an example. Here you have a computer with a cache, a dynamic RAM, and a hard disk hierarchy. The hit rate for the cache is 95%. Hit rate for dynamic RAM is 98%, and almost everything is going to be in the hard disk. The read latency is 2 nanoseconds for the cache, 50 nanoseconds for the dynamic RAM, and 10 milliseconds slower, so 10 milliseconds for the hard disk. Now the question is, what is going to be the average latency of executing an instruction involving a memory read? So you're trying to get data from the memory to the CPU. So 95% of the time, we are going to find that particular word in the cache. So for 95% of the time, we are going to have a latency of 2 nanoseconds. And if we miss the cache, that means 5% of the time we are not going to find it in the cache. In that case, we are going to have to look in the dynamic RAM. 98% of that 5% is going to have a latency of 50 nanoseconds. So we add that term. And then 2% of that 5% is going to go straight through and will need to access the hard disk, which has a latency of 10 milliseconds. So we include that particular term. If you add all of that up, the average latency for an instruction is going to work out to be close to 10 microseconds. Now let's see if we can improve that. And we are trying to improve that by adding a solid state drive, and we are going to be adding that block right here. And we are assuming that the solid state drive hit rate is 99% and the read latency is 80 microsecond. So in this case, what is going to be our average latency? The first two terms are going to remain as is because the hit rate and the access latencies of the first two levels did not change. But when you added the solid state drive, then you had 5% missed here, 2% missed there, and then 99% of that 5%, 2%, or 5%, 2%, 99% will have the latency of 80 microsecond. So that has to do with the solid state drive. And the last term is going to be when you have a rare access to the hard disk drive, which is 5% miss there, and miss in the solid state drive, multiplied by the latency of that particular level, 10 milliseconds. So that's going to add up to 184 nanoseconds. And numerically, if you calculate that out, it's going to be 50 times faster than what we had over here. So if we have more levels in the hierarchy, we are going to benefit from that as long as they have less latencies. All right, we are going to stop here in this particular lecture, and then we'll pick it up with cache and the memory in the next one.